This is the second installment of our discussion of Chapter 4 of our Human Anatomy and Physiology text. We're right in the middle of a survey of all the different tissue types that make up all the organs and organ systems of the body. In the last section, the last installment, we finished up our survey of the epithelial tissues, the first of 4 general categories of tissues. And in the last section, we also introduced the sort of arrangement of things, the components, the structural elements of connective tissues. We said the connective tissues, unlike epithelia, are not very cellular. They contain some resident cells surrounded by an extracellular matrix of fibrous proteins and some ground substances, so-called. And so now that we've kind of established that, and we've actually seen what a proteoglycan is like, the ground substance component in some of the connective tissues, let's go on and really look at each of the connective tissues in turn in a little bit more detail. So the first of 4 types of connective tissue is connective tissue proper. And here is a little mini outline showing you the different types of loose connective tissue proper and dense connective tissue proper. So those are the 2 major categories, and we'll now just run through and see what each one of these is like, what the resident cells are, and what the protein fibers are, and so forth. And then we'll go on to the next major connective tissue category. So the very first category, loose areolar connective tissue, is kind of it is, just as it's named, a loose weave of protein fibers. There are predominantly collagen fibers, a very important building material, probably the most prevalent building material in your entire body. So collagen protein is shown here, and we also see some elastic proteins. Elastin is a protein that makes up these elastic fibers, and the difference is that collagen resists stretch, whereas elastin, when you stretch those fibers, they recoil. Recoil just means that they snap back to their original dimensions, sort of like a elastic thread would do in your garments. So that's the sort of the main structural material that's present, and the resident cells that can secrete all these protein fibers and the proteoglycans that form kind of a pliable, gelatinous goo around all these fibers are fibroblasts. So those cells' job is to create this tissue and maintain this tissue, repair it when damaged and so forth. But there's other cells that are found in this type of tissue. There are white blood cells, defensive white blood cells, for example. Here is a macrophage, a phagocytic cell that can recognize foreign material and engulf it and bring it into the cell, phagocytosis, and then digest it and kill it if need be, if it's a invasive bacteria, for example. Also, debris after tissue injury is often cleaned up by macrophages. Lymphocytes are immune cells lying in wait for their moment when they can really defend the body against a specific invader. So lymphocytes are quite numerous in tissues like this, and again they're waiting to be discovered through a process that the immune system uses to fight against specific types of invaders in the body, infections in the body. Mast cells are a type of white blood cell that upon tissue disruption or challenge releases histamine, and that causes inflammation. Inflammation is an important sort of prerequisite for wound healing, tissue healing. So if there's injury to a tissue, mast cells will degranulate, initiate inflammation, and then right at that time the repair process begins if it's allowed to take place. Here's a neutrophil. That's a white blood cell that is normally found in the circulation, not in a tissue like this. But if you see a neutrophil out here, that means that there's somewhere around here is a damage to a tissue, inflammation going on, and possibly an infection, and that neutrophil has, in the presence of certain chemical signals, has left the circulation and is on its way to fight against the infection that is starting up in this area. Here's a blood capillary from whence that neutrophil would have arisen, and areolar connective tissue is very rich in capillaries. Areolar connective tissue see if we can see where we might find some areolar connective tissue. I'm going to come back to this slide in a second. Areolar connective tissue is found under all epithelia. We just finished a survey of all the different types of epithelia, and now we can generalize. And so if you're wondering where some areolar tissue is, look at any micrograph showing an epithelium and the neighboring tissue. The next deepest tissue will be areolar connective tissue. The thing that triggered my interest in showing this slide and mentioning that is that epithelia are avascular. They have no blood vessels of their own. Even a stratified or multi-layered epithelium like this, the epidermis of the skin, has no blood vessels of its own. All of its oxygen and glucose and other nutrients has to come from capillaries located in the areolar connective tissue next door. So yeah, it's very vascular. Proteoglycans are the ground substance. We looked at proteoglycans last time. They're an enormous protein and carbohydrate complex that hydrates a lot of water and makes like a pliable gel around all these fibers. Adipose tissue. We may see some adipose cells distributed in this areolar connective tissue. Here is a prototypical areolar connective tissue. A picture like this is often used to illustrate areolar tissue in manuals for teaching histology and teaching an introduction to tissue types. I prefer to have you learn various tissue types in the context of the organs in which they serve their purpose. So I would not use a picture like this to illustrate areolar connective tissue. I would use something like this or some other organ that we're looking at, so that when you're looking at the micrograph, you're seeing multiple tissue types and you can recognize the organ in which all these tissues reside. So this is the epidermis of the skin, and this is what's called the papillary dermis of the skin. We'll come to that. We'll study the skin in detail in Chapter 5. But I'd rather you recognize the skin and know that that is the tissue neighboring that epithelium, and then in a little bit we'll talk about the next tissue deeper to this areolar tissue within the organ of the skin, and all the while you'll be able to recognize geographically where you are by seeing that that keratinized stratified squamous epithelium. So that's my strategy. So there's just some words, a word slide that details out the things I've been talking about in that cartoon picture of areolar connective tissue. Okay, so the next type of loose connective tissue is adipose tissue, and adipose tissue is fat. Adipocytes are the resident cells. That suffix cyte just means cell, so adipose cell, adipocytes. And the adipocytes are shown here, and they're essentially just a container. There's hardly anything to it at all, except for this container, this hollow space in here, which used to contain some triglycerides mainly, what we call fat. Like if you think of vegetable oil, that's what kind of thing you'd find inside this container. There might also be some other types of lipids in there, but this is a storage reservoir of triglycerides for the most part, and it's a tremendous source of energy when needed. It insulates the body from heat loss. It's found underneath the skin of the entire body. So under the skin is some adipose tissue, and it acts as a shock absorber. When we bump into things, it prevents us from causing fairly deep injuries, bruising, to say the muscles and bones that lie underneath the skin, because they have this nice cushioning layer of fat in there as well. Fat also makes a great packaging material for glands. Here we see quite a bit of adipose tissue within the mammary glands, but also there's adipose tissue in the bone marrow, around the heart, around the kidneys. So it's kind of like packing peanuts around the eyeballs, packing peanuts for the organs of the body, if you will. We'll come up against some more applications of where we might find some fat tissue in the body as we go along. Fat tissue is part of the sculpting of the female body. The secondary sex characteristics of the female body include some accumulation of fat, say in the hips. So that's another area where we may find some adipose tissue. The third kind of loose connective tissue proper is reticular tissue, and it's what we call immune tissue or lymphoid tissue. It's a tissue that's comprised, in this case, of reticular fibers, and the resident cells are reticulocytes, so reticular cells. They secrete these fibers and maintain it, And then the fibers create a scaffolding upon which white blood cells can cling. So white blood cells have receptors that allow them to attach themselves to this fibrous scaffolding, and so there's lots and lots of lymphocytes, especially, that's the majority of the cells, macrophages, which we've already encountered, dendritic cells, which are a cell much like a macrophage, a phagocytic cell that can recognize foreign agents like bacteria that have gotten into the body and activate an immune response when that happens. So these are some white blood cells that might be seen in some lymphoid tissue, a type of reticular tissue. The spleen, bone marrow, lymph nodes, tonsils. Those are places where we would encounter this sort of tissue, this reticular tissue. We'll talk a lot more about reticular tissues when we talk about the immune system in chapter 21. All right, so those are the loose connective tissue proper. Now we come to 3 types of dense connective tissue proper. And this is the first category. It's called dense regular connective tissue, and it's a great name for it because what it is some very heavy duty collagen fiber bundles that it's a fibrous protein that is very tough, resists stretch, stronger than steel, weight, dimension for dimension. And here we see all heavy-duty collagen fiber bundles arranged in parallel. They look a little wavy. That's probably an artifact or a result of the fixing and staining process after this was cut from the tissues. But it's very orderly. And tendons that connect muscles to bones are made of this dense regular connective tissue, just lots of very tough collagen fibers that weave into the muscle tissue among all the cells and jacketing around the whole muscle organ, and then fasten onto a bone to allow the muscle to pull on the skeletal levers and allow us to move our skeleton around. So tendons are dense regular connective tissue. Ligaments are similar applications of dense regular connective tissue attaching bones to bones. Joints are inherently unstable, meaning they're not very strong compared to the bones that they attach to, and so ligaments help stabilize the connections between the bones so that joints can only move in sort of prescribed manner, prescribed planes and directions. So ligaments connect bones to bones, typically forming a type of joint in each case. Here you can see this purple bit is the flattened nucleus of a fibroblast that's kind of packaged in there among those collagen fibers. That's the resident cell, just like in irregular connective tissue. Fibroblasts are the resident cell of dense regular connective tissue. This tissue resists stretch in one direction. If we were to grab it from above and below and pull, it would split apart, if you imagine such a thing as that. It's not meant for that kind of a tensile strength. It's meant for resisting stretch from between a muscle and a bone, for example, and that's what its strength is. Whereas a similar tissue called dense irregular connective tissue is made up of also heavy-duty collagen fiber bundles arranged in every which way. There's just collagen fiber bundles going in every direction, all interlaced with each other. And so it produces a tissue that can resist stretch in any direction. It's extremely tough. And it's what the bulk of the thickness of your skin is made of. Your skin can resist stretch. You can really bump it on things and catch it on things, and it's very, very tough. So the mechanical strength and support for the skin comes from dense irregular connective tissue. That's the dermis of the skin. We'll talk again a lot more about the dermis when we're studying chapter 5, which is all about skin. Also, dense irregular connective tissue is found in the joint capsules. Most of the freely movable joints in your body are jacketed and closed entirely by a capsule, the outermost part, which is called the fibrous capsule, and it's this tough, dense irregular connective tissue to kind of give some additional stability to the joint in addition to the ligaments. And it also serves to enclose that joint, so we have a joint cavity which is separate from all the other compartments of the body. So that's dense irregular connective tissue. Also, fibroblasts are the resident cells. And finally, our third type I forgot about this slide in between here. We have a slide going back to the skin as I promised, showing the keratinized stratified squamous epithelium here. the areolar connective tissue, which is part of the dermis of the skin. And then, unfortunately, it's cut off. It would be nice if we could almost see the relative proportions, but deep to the areolar tissue is the thickest part of the skin, so it would extend well below this micrograph. The dense irregular connective tissue, which forms the largest part of the mechanical support for the skin itself. So a very thick swath of dense irregular connective tissue forms the reticular dermis, we call it. It is odd that we use the term reticular dermis to refer to this deepest part of the dermis when we just finished defining reticular connective tissue, so I just wanted to call your attention to that so that you don't get confused between the two. Reticular connective tissue is that sort of light, loose connective tissue where the white blood cells are perched on the reticular fibers. The reticular dermis is made up of dense irregular connective tissue proper. Okay, so now we come to that third, finally, category of dense connective tissue proper. It's elastic connective tissue. And this is stained a little differently from all the slides we've been looking at, or most of the slides we've been looking at, in such a way that we can see the elastic fibers showing up black in this picture. And so all those squiggly lines are bundles of elastin protein. And this tissue is found in the walls of the largest arteries. And the job of the heart is to force blood out into those largest arteries and stretch them. They get all kind of stiff and tight. There's a lot of pressure in there. And then the heart takes a rest while all that elastic tissue that's been stretched pushes the blood through the vascular system. 2/3 of the blood flows through the vascular system in response to recoil of all this elastic tissue in those large arteries. So that's a cool thing. Here's a little picture that looks a little bit like a deer antler, but it's showing you the heart and the aorta, the largest artery of all, with some of its branches arising here. And all those are elastic arteries they have a lot of this elastic tissue in their wall, in the tunica media. Okay, so that's all the connective tissue proper types. I should have mentioned in here are also fibroblasts as the resident cell. Now we come to the second category of connective tissue, which is cartilage. And cartilage, amazingly, is almost the same exact composition as, say, areolar connective tissue or dense irregular connective tissue. It's collagen. So let's take a look at our first type of cartilage. What we're looking at here is hyaline cartilage. And hyaline cartilage has as its fibrous protein collagen. As we said, this is starting to become a theme, right? Collagen is extremely prevalent building material of your body. The resident cells are chondrocytes. So that prefix chondro means of cartilage, so you're going to hear that a lot in the context of cartilage. So chondrocyte is just cartilage cells. Makes sense. Well, cartilage has a different type of proteoglycans in the ground substance than connective tissue proper, and it's a type of proteoglycan that is so negatively charged and hydrates water and becomes so stiff that it has a composition more like hard plastic almost. It's a tougher material than connective tissue proper, and in fact it is incompressible. So whereas connective tissue propers tend to resist stretch, or allow stretch in the case of elastic tissue, this material resists stretch but also resists compression. It has kind of more of a three-dimensional character to it, and so it's kind of stiff. Chondroitin sulfate proteoglycan is that stuff that's is prevalent in cartilage. So you hear that chondro in there, chondroitin sulfate. The resident cells, because this stuff is so dense and stiff, need a place to be, and so whereas fibroblasts can kind of wander all around among the fibers of dense irregular connective tissue, for example, the chondrocytes live in hollow spaces within the tissue of cartilage called lacuna. So an individual lacuna with an A, plural lacuna with an AE at the end. So these are lacuna with chondrocytes residing in them. That's a giveaway. When you see those little blister-like clear spaces in the tissue, that is a giveaway that you're looking at cartilage. Hyaline cartilage is has the finest extracellular matrix of all the three cartilage types, and it's so fine that you typically cannot see the individual collagen fibers here. They're so fine that you just see an amorphous pink or gray background around these lacuna of chondrocytes. Where would we find it? Feel the bridge of your nose. That stiff kind of square edge bridge of your nose, that is hyaline cartilage. Your Adam's apple, quote unquote, your larynx is a box made of hyaline cartilage in your throat. Your ribs are attached to the sternum by bars of hyaline cartilage, so they're called the costal cartilages. As you may remember from studying chapter 1, costal means of the ribs, and so these are the rib cartilages. Allows your rib cage to have a lot of flexibility and give to it so that we can move those ribs around and bring in lots of fresh air as we ventilate or breathe, bringing air in and out. One last thing I'll say about hyaline cartilage. In those freely movable joints, the ends of the bones have hyaline cartilage. It's glassy smooth on the ends of the bones, then covered by some lubricating fluid, and when the bones are placed in juxtaposition with that super smooth hyaline cartilage on the ends of the bones, the so-called articular cartilage, it gives a very low friction surface for the bones to rub on each other. So articular cartilage just means joint cartilage is found on the end of the bones where the joints form. Okay, so the next type of cartilage we'll take a look at is called elastic cartilage, and it's kind of analogous to elastic connective tissue proper. It's cartilage in the way that hyaline cartilage is. It's got a lot of collagen fibers. They're a little heavier duty, but mostly what it has is elastic fibers. So it has a lot of recoil ability. It's very tough and strong, but it has recoil ability. And if you feel the pinna of your ear, this outer part of your ear, and how pliable it is, that's because it has elastic cartilage as the sort of inner construction of the shape of your ear, and also your epiglottis is a little flap trap door that folds down and closes over top of your larynx, your voice box, every time you swallow. Those are the functions of elastic cartilage, and you can feel a big difference between the sort of pliability of that elastic cartilage and the stiff hyaline cartilage in the bridge of your nose. Again, here we've used a stain that will cause the elastic fibers to become prominently exhibited in either navy blue or black, whatever that is. I can't tell for sure. So that is the second of three cartilage types. The toughest, heaviest duty type of cartilage is called fibrocartilage, and fibrocartilage has very, very heavy duty collagen fiber bundles indeed, and you can see them here. You can see the thread-like nature of all those bundles of collagen, but you can still see the chondrocytes in their lacuna, which again is a giveaway that you're looking at some kind of cartilage. Nothing else looks quite like this. And again, this is not the typical stain that's used in most of the micrographs we have in this collection. It's designed to help us see those fibers a little more clearly. But this is fibrocartilage. Where would we find fibrocartilage? One place we'll find is in the intervertebral discs. This obviously is the spinal column, the vertebra, are these irregular bones here, and then in between the bodies of the vertebra are little cylinders of fibrocartilage, enormously tough building material indeed, that gives some flexibility to our spinal column, but very much restricts how much movement there is. It's a shock absorber for when we walk and run and jump. It allows us to twist and flex the spinal column, but there's other joints also in the spinal column that kind of define the range of movement of the vertebra relative to one another. But that's what's actually forming the primary joint between the bones is fibrocartilage. Intervertebral discs. There's another type of symphysis. That's a joint made up of fibrocartilage between two bones. The two pelvic bones, where they come together in the front of your pelvis, you can feel on the front of your body there's like 3 points of a triangle. At the lateral upper part of your hips, you can feel 2 points where the iliac bones come to the surface, and then you can feel below that where the two pubic bones arc towards the front of your body and meet at a joint formed of fibrocartilage, the so-called pubic symphysis. Sounds like you're speaking with a lisp. Symphysis with a PH. So it's just a type of joint formed of fibrocartilage. Allows a small amount of movement between the bones, but it's not the kind of joint that we typically think of as a freely movable joint. And finally, or not finally, we come to bone, the next type of connective tissue. And bone is, again, very similar to cartilage and to some types of connective tissue proper. It's made of cartilage mainly. Of collagen. Collagen is that ubiquitous building material, that fibrous protein that is found in so many of these connective tissues. It's extremely strong, but yet has some resilience. It's flexible, it resists stretch, but it's bendable. And in the case of bone, the collagen fibers are ensconced in a hard, stiff mineral ground substance called hydroxyapatite. It is, in fact, a mineral. Calcium phosphate crystals, rock-like crystals. It's like taking a bunch of collagen fibers, arranging them in a unique way to form the units of bone structure, and then saturating them with cement and letting it harden. So the fibers are collagen, but there's the ground substance has hydroxyapatite. It's extremely hard and stiff. Strong. So your bones are obviously very different in properties. So as I was alluding to at the very beginning of this discussion, the ground substance plays a huge role in the qualities of the tissue. Pliable, the proteoglycans and connective tissue proper. Incompressible, proteoglycans, chondroitin sulfate and cartilage. And now hydroxyapatite, hard and stiff in bone. But all three types of tissues are made largely of collagen fibers. In the case of bone, the resident cells need a place to live also. Osteocytes, osteo is a prefix that means of bone. Osteocytes, bone cells, right? So we have osteocytes living in lacuna. That's what these little black smudges are. They are sort of flattened out bone cells living in hollow spaces called lacuna in the bone. What you're seeing here, these circular structures represent long cylinders. I get my hand on the picture. Long cylindrical structures in the shaft of this long bone. There's long cylindrical structures that span the length of this bone, and they're all packaged in there like a bundle of sticks, which gives it an enormous strength. Each one of those cylinders is actually made up of many cylindrical concentric layers, and so this is called lamellar bone oftentimes. Anyway, we'll have the chance to talk about bone again in a later chapter. In chapter 6, we'll talk about bone tissue and so forth. But just a little preview. So what we've done is we've cut through in cross-section, and so when we start with a cylinder and you cut in cross-section, you wind up with circles. Incidentally, you can see in the middle of these, in this core of these cylinders, we see a hollow area filled with some substance. It's called the central canal, and there's blood vessels that penetrate those canals and provide nutrition for all those osteocytes trapped in their lacuna within this extra hard, stiff bone tissue. Finally, now we do say finally, the last category of connective tissue is called blood. And how odd to think of blood as a connective tissue. We have resident cells. We have red blood cells primarily, erythrocytes they're called. We have white blood cells of 5 different types, which are defensive cells of various functions. And then we have some platelets in here. Platelets are cell fragments important for blood coagulation, blood clotting, floating around in a water-based substance called the plasma. So in the blood vessels, we'll find blood cells immersed in water, a very highly concentrated protein solution of water, incidentally, also with a lot of salts and so forth, yet it's a watery substance called plasma. So how is that like a connective tissue with a fibrous extracellular matrix? Well, when the blood vessels are torn open, there is a regulatory, a homeostatic mechanism invoked by which the blood will clot. Platelets, which are these little cell fragments, will become sticky and aggregate at the place where blood is escaping from the blood vessel and plug it right up, and then some proteins in the plasma will solidify into a gel, and that's what we call a blood clot. That's what prevents more and more blood from escaping from the injury of the blood vessel, and that's a homeostatic mechanism to keep the blood in. It's so important and famous that it has its own name, even though it's a homeostatic mechanism. It's called hemostasis, in that case in which the blood is going to stop flowing out of that opening and stiffen and clot. And so there's stasis, means stoppage, at that place where the blood vessel is damaged. The flow is going to stop, and we're going to let some repairs take place before we open up that area once again. So that's the connective tissue of blood. It looks like a connective tissue when it clots. Fibrin is the fibrous protein that forms when the gel of the coagulated blood forms, when the plasma forms. It's a sticky protein that forms fibers spontaneously upon activation of coagulation and sticks to everything so that blood will stop leaking out. So that concludes our survey of the connective tissues, and then the last section of our chapter we'll go on and look at 3 types of muscle tissue and nervous tissue, and we'll have concluded our study of all the tissues that make up all the organs and organ systems of our body. So it's a fascinating journey. It's not that crazy long, and now we are poised to understand the anatomy and especially the physiology of all the organs as we observe what tissues are found connected together to form each one of those structures.